Okay, welcome to today's sustainability seminar. My name is Nancy Holm. I'm Assistant Director here at ISTC and a seminar organizer along with Beth Mashesky. The theme for this fall's seminars was contaminants in the environment, and this is the last seminar in our series for the semester. Seminars are recorded and videotapes of the seminars are archived on our website, usually within a week after the seminar. We have over 150 seminars available on our ISTC website. We will begin today's seminar, and I would ask everyone here in attendance to please silence your cell phones. And also we will hold questions till the end of the presentation, and then I'll come around with the microphone so we can record those and everyone can hear those questions also. For those viewing online, you may type in your questions at any time, and then we'll answer them at the end also. We're very pleased today to welcome as our speaker Dr. Scott Spak from the University of Iowa. Dr. Spak is an assistant professor holding joint appointments with the Urban and Regional Planning, Civil and Environmental Engineering, and the Environmental Policy Program at the Public Policy Center. He teaches courses on U.S. and international environmental policy, dynamic systems modeling, and urban growth. Dr. Spak develops and applies numerical models to study the intersection between human activities and environmental change. His research interests include aerosol impacts on climate, high-resolution coupled Earth and human systems modeling, effects of urban form and policy on air quality, and air toxics. Dr. Spak received his AB degree in engineering sciences from Dartmouth and his PhD in atmospheric and oceanic sciences from the University of Wisconsin-Madison. Today, Dr. Spak will discuss his work on PCBs in Chicago, sources, transport, fate, exposure, and policies. With that, Dr. Spak.
So my first department seminar as a grad student was right after the 2004 presidential election, the day after. And my first forecast briefing for a major field campaign was the day after the 2008 election. So it appears that I have like this history of giving uplifting talks about environmental chemistry and atmospheric science immediately after presidential elections. I'm glad to keep that tradition going. And so in the context of talking at Illinois, I was focused on Illinois' special history with regard to PCBs and the special opportunities that we have to understand them, to use what we learn here about how they work in the environment, sources, fate, as a means of understanding how PCBs can be studied, remediated, understood globally and nationally. So I'll try to, in every component of what we do in this talk is focused on Chicago and Illinois, show how we can take that out to a national or global scale. So as an atmospheric chemist, atmospheric chemical modeler, a lot of what I do is the Cotton Eye Joe transport and fate story. And for PCBs, we think of this within a much broader context. Brookstrom et al. Have the story of what are the big systems that are the sort of natural infrastructure that supports our species and all other species. And among them, these bars are their first guess at where we are. That black line is the natural planetary level at which the Earth is able to sustain stuff. And their first guess and the second guess and the third guess have all had big question marks for atmospheric aerosol loading and chemical pollution. And a lot of these systems, like climate change, can only be addressed globally. You have to have the full global picture. And this group and all of the work that has come out of it has said chemical pollution is a bottom-up story. We have to understand what happens locally. We have to look at the threshold and tipping points locally and then aggregate them to understand the global story. So when I, as an atmospheric scientist, looked at this, I said lots of people are looking at what is the state and evolution of the system, making measurements, using models to blow stuff around, multi-compartment modeling, transport and fate in general. What are the drivers of these things, the activities that people do, what are the impacts, and then what are the potential solutions, and then decision support. How can we tie all those features together so that we can make wise decisions? And doing so at the local and urban and regional scale. In some of those is the frontier, and I said I wanted to work on the frontier, and PCBs were a great place to do that. So whenever I talk to regulatory communities, they say PCBs, that's a has-been chemical. It's the first legacy organic, persistent organic pollutant that we made. Why should we still care? And I said, this is the reason why we can't have nice things. This is why we can't use lots of places and reuse urban and Great Lakes lands and tributaries. This is why we can't eat fish from this part of the world for the next at least 150, maybe 500 years. It was one of the original reasons for TSCA, and it's still out there. And so we still have brand new news about PCBs. And from my big picture perspective, if we want to understand chemical pollution overall, PCBs are our best toy case. They're a bad actor in every way. Endocrine disruption, known carcinogen, linked in large cohort studies to autism, ALS, polycystic ovarian syndrome. I am the manager for the Iowa Superfund research program's Twitter account, and so I see all of the news and all of the papers that come out each day and try to share them and try to take them all in. And if there's something bad that a semi-volatile compound could do, PCBs tend to do it. So if we wanted to have a toy compound that we could study that would be representative of types of impacts, toxicology, sources, many, many sources, PCBs are not only the first and longest legacy compound, but the one that's most representative of all of the emerging compounds in the future in terms of how it behaves in the environment, all of its many sources, and if we can figure out how to clean this up, we can figure out how to clean up other stuff. And so, of course, Great Lakes areas of concern, most of them due in part or exclusively to PCBs. In the past 2 months, we've heard that microplastics have been found in all Great Lakes tributaries in every sample. They concentrate PCBs and other semi-volatile compounds out of the water to about 10,000 to 100,000 times the concentrations in the overlying water. And most of these are coming not from those microbeads that scrub your face, but from our fleece clothing. So if you do field work wearing a fleece jacket, you're a recidivist offender at getting plastics into the environment. On the other hand, this could be a growth potential for how we remediate, because they'll just soak up persistent organic pollutants in situ. Other Great Lakes area of concern stories: 3 Wisconsin tributaries to Lake Michigan were recently studied for fish tumor rates, and they all were part of areas of concern, all had elevated tumor rates, and all of those included a strong correlation with PCB and other PAH concentrations. And so we haven't seen, if this is a has-been compound, we haven't seen these compounds really declining in the environment as much as we might expect. We've seen declines in fish, in bird eggs, and in the waters of the Great Lakes. But in the air, which is the main source to the lakes these days, and our best guess since the 90s has been that the lakes are a greater source to the air than vice versa, but in terms of all sources, tributaries, contaminated sites, air, it's air from urban areas and from the global background that are the biggest source to the lakes these days as a new source. And so this is in Chicago at the Eavon site at Illinois Institute of Technology. Now it's called Illinois Tech, right? And so we have the black line, moving average concentration in the air from 1996, this is total PCBs, from 1996 until 2008, and it's essentially the same. Air concentration is not going down. What is changing is that the average molecular weight is rising. The more volatile stuff in secondary sources and primary sources has come off of the built environment, and so what's coming off now is that higher molecular weight stuff that as the temperature changes, you're gradually getting those heavier compounds coming off. So we can expect over a very long period of time, and you can do some modeling to try to figure out how many hundreds of years we're talking about. Over a very long period of time, we can expect these concentrations to go down if there are no new sources, if it's just a matter of existing soils, built environment, contaminated sites, gradually moving from there to the air to the water. And of course, PCBs are an issue now in schools, in the Hudson River, and in every West Coast port. So, national news controversy in the New York Times, in Malibu, major legal case. We worked with America Unites, formerly Malibu Unites, to try to provide unbiased information about PCBs in school, about how much is there, how can you test, what is a safe amount. Our center, Iowa SUPERFUND, which is focused on PCBs, has found that at least in East Chicago, Indiana, schools are the biggest source of airborne exposure to children. Of course, some people will say that this is atrocious. Any amount of PCB exposure in schools is too much, and we're trying to figure out, well, how much is there in a typical schoolroom? Does it change by place? How can we clean it up? And about what level starts to become an important factor in total exposure from all sources. Similar things have happened in China. We have politicians locally and nationally. This is Senator Markey, and here's Cindy Crawford with elected officials attempting to figure out how to get new legislation in place on PCBs in school. In May, big sold-out charity event. Expect to see more on PCBs in schools over the next few legislative cycles in Congress. So we know that the U.S. regulates and cleans up PCBs and other legacy toxics in a few different ways. SUPERFUND, Great Lakes Regional Initiative, $18 billion a year industry, cleaning up the most contaminated sites. So clean up the most contaminated sites. Clean Air Act and RCRA, preventing new emissions, no more new spills, no more new sources. And then gradually figure out how to get rid of the rest, this unknown quantity of other sources like electrical equipment and transformers, that we have a voluntary national transformer registry, but all of these other unknown sources, we don't know how much of them there are, we don't know where they are, and we don't know how much PCBs they have or are giving off into the environment. And so I think of this in context. In about 200 years, you should be able to look out from the Quad Cities or from Peoria out west to Riverside, Iowa, where our species is supposed to be building its future spacecraft, interplanetary, interstellar spacecraft. Big industrial site. We need to figure out how to clean up industrial sites before then. Our existing ones, because the PCBs that are currently at contaminated sites are expected to still be around then if we don't do that, as well as to prevent new industrial activity from creating new contaminated site issues. So we can learn from PCBs as one of our first signals on how to do this. And Chicago, in addition to being my hometown, is a really great place to study it. So just looking at the Chicago flag, all 4 of the stars represent events that relate to land use. The 2 water bodies are Lake Michigan and the Chicago River, also known as the Chicago Sanitary and Ship Canal, both contaminated with PCBs. We've seen from time series analysis, again at that Illinois Tech site, that there are several different signals in that trend, well, not really a trend that I showed, of what's happening in the air. And some components of the total PCB signal are increasing, some are decreasing, some we don't know. We know that there are big spatial gradients within the city, and we know that when we look at water concentrations observed and modeled in Lake Michigan, we have to change the color scale to represent what happens right near the city. So if we wanted to look at a representative megacity globally and a representative US city that has manufacturing history, has been a major transport hub for PCBs coming from other parts of Illinois where the greatest bulk of PCBs were ever made. We have a really long-term monitoring history here from IADN and from other monitoring groups. And we know that there's urban variability, and we can use some land use regression to attempt to describe that signal. And we can try to guess why certain sites have higher concentrations than others, but it's really not explained just by point sources or just by land use. So when I first got started with PCBs, thinking from a planning and GIS perspective, I said, let me throw all of my land use data at the concentrations we have so far. That should explain something. And it was all journal of negative results. I've since refined that, and I'll show some results. But land use alone and point sources don't explain what we see in the air in terms of intra-urban spatial variability. And so when I began working with Project 4 of the Iowa Superfund project with Professor Carrie Hornbuckle's lab, they had started a whole bunch of opportunistic sampling. They had an asthma clinic van that went around to schools, public and private schools, and would, while they had children tested for asthma, take high volume samples for about 8 hours on the site. And so that's these purple and sites in Chicago. But for doing understanding sources, they were opportunistic. It's wherever a school is. And so when I began with this project, I started setting up at Illinois and US EPA population-weighted SLAMS monitors for where ozone and fine particles and other criteria pollutants are also tested, and we got permission to set up passive air samplers. That's these flying saucers with a polyurethane foam disc inside at their sites. And so we were able to get this ring of exurban sites, a whole bunch of suburban sites representing different land use characteristics, some of them 1960s development, some of them 1940s development, some bungalows, get an urban to regional, urban to rural transact going into the city, see what happens as you get closer in, and then a few different point source sites near Joliet Arsenal and Waukegan Harbor where we have known contaminated sites. So we set up the world's largest urban passive air sampling network for persistent organic pollutants, and we now have about 800 samples, about half of them analyzed. And all of them, we have archived samples. So if you're interested in studying what happens at the urban scale in Chicago, let's talk, because we have samples that represent these spatial gradients, that represent different recent years, and the ability to pull out anything that you can find from this passive air sampling mechanism. And we know that the profile in Chicago looks like a combination of aerochlor and non-aerochlor sources. So we have the obvious electrical equipment, dielectric fluid story, as well as some non-aerochlor compounds like PCB11, which is found in paint and pigments as an unintended byproduct of the manufacturing process. And it's one of the highest concentrations, and it's found in all samples. And so when I started with this project, we knew about the same as what this group has known, that their PCBs are present in paint and sediments and a whole bunch of other unknown sources, that they can be quantified from contaminated sites like the Indiana Harbor and Ship Canal, but not from the sources, all of the sources on the ground that go into this airshed. And that each congener has different properties, sources, and fates. So all of the analytical work from the samples that I get to use for this is at the congener scale, so that we can look at the effects of individual compounds and pull out what the aerochlor and non-aerochlor sources going into them are. So we said for the next 5 years what we'd like to do, and that's 2015 through 2020, is figure out what these sources are, aerochlor and non-aerochlor, figure out what's coming off of a contaminated site into the air, figure out the compounds that are sources in indoor air in both public buildings and in homes, and determine the chemical and physical properties of hydroxylated PCBs, the first breakdown product in the environment, going along with other projects from Iowa Superfund that are looking at metabolic processes and breakdown products in people and other animals. So a lot of what I do is building tools and adapting other existing tools to help solve this problem. And in this case, a few of those tools will be, as an atmospheric chemist and atmospheric chemical transport modeler, different ways that we try to blow other compounds around in the environment that really haven't been used very much for PCBs. And one of my favorite tools for the job, and one of my favorite ways to address this, is to take regulatory models and use them exactly as regulators use them. Try to get novel compounds to be modeled with the same accuracy and precision and same level of trust as criteria pollutants in regulatory context, so that we can have that same level of faith in the results. And in this case, if we wanted to do chemical transport modeling at the urban to regional scale, we would use CMAQ, the Community Multi-Scale Air Quality Model, which is open source, modular, supported by US EPA. And our friends to the north in Canada at Waterloo University did the first study trying to put PCB chemistry into CMAQ, and they did a 36-kilometer scale model. And they allocated existing national scale emissions and source estimates to population, because absent any other spatial surrogate, population is their best guess. So this looks a lot like, if in red would be the Democratic presidential election result, is a population-weighted story. And the results in the chemical transport model output look like that. You get big blobs over every city. And so then this can tell within order of magnitude or so concentrations in the air for, they use 22 PCB congeners. It doesn't tell you how to clean up that air. It doesn't tell you what the sources are. And we're not even sure whether that's a really good spatial surrogate. So we have all the tools to be able to do this, if only we know the sources and emissions. And this is our low performance bar. Getting order of magnitude is about what a current regional scale chemical transport model can do, and it's limited by the emissions. So in 2009, 2010, when I was first approached, hey, how would you model PCBs? I had this idea that we would do local modeling for individual contaminated sites, nested regional modeling going down to 1 kilometer over Chicago, take whatever emissions inventory already existed from TRI and other sources, put it in there, and do some variational data assimilation and emissions inversion to perfect those emissions. This talk is the story of what had to happen just to be able to get started on this. And so the first part is to figure out how we can sample the entire city, set up that monitoring network, and get air samples that can play well with models. And those passive air samplers are great for playing well with models because they take an integrated sample that you can compare to an integrated hourly modeling result. They're cheap, much less expensive than a high volume sample. And so we wanted to figure out how well we can estimate the sampling rate and the concentrations and reduce those errors. Because if we, just from monitoring, we can get the observed spatial variability, we can locate any potential hotspots, we can look at the impact of local meteorology. And high volume has the sampling challenge that's logistics. It's expensive, you have to send people out there frequently to change the pump, to change the filter. You get short-term samples. Passive air sampler, much less expensive, but you don't know what the sampling rate is. So the traditional method has been to set up some sort of similar deparation compound, spike your foam disk with it, see how much comes off from the puff out to the environment, and figure that the uptake of similar stuff was the same. That tends to be actually rather expensive too. When you consider that you have to get a carbon or other isotope labeled semi-volatile compound, spike a known amount of it onto this, a large amount, because you're going to be losing it over 60 to 90 days, and then do all of the blank, field blank, lab blank, sample analysis for those compounds as well as everything else you find, you're talking somewhere between, depending on what your methods are, an extra $100 to $1,500 per sample just for knowing that sampling rate. And once you know that sampling rate, you still have all the analytical stories of trying to figure out the lab and sampling uncertainties that go into that. So you're multiplying your analytical uncertainty for your sample with your analytical uncertainty for your deparation compound. If those are each 20%, your error bars get huge really quickly, and it's expensive. So we wanted to ask, in addition to wanting to know what do these things really measure, what are the error bars, how can we reduce them, what does this really mean, we wanted to figure out how to use them, how to compare them with a model, how to estimate and reduce their uncertainties. And so we built this hourly, really complicated first principles approach to how do semi-volatile compounds go off the air onto the filter. I won't bore you with the math, and I'll just show you the results. We now have a way to do this with both observed meteorology, like from any airport, as well as with model meteorology. This is model results across the Great Lakes region and over the Chicago area for those flow rates. Just with a model, takes about 3 seconds to run for any sample, getting hourly sampling rates and hourly uptake so that we can see, did it go nonlinear? Did it saturate? And what is the average and how did it vary with meteorology? We didn't have any way to calibrate what happened over the Great Lakes with really high wind speeds, so they're like blank here. But we see even at the urban scale, there's big gradients in this sampling rate. So typically, people who do passive sampling have said, someone else, you found one number, 4.5 meters cubed per day, so we're going to use that. And what we have found is that these things actually vary. You can see the effect of the built environment on temperature and wind speed here. This is January at the top and July at the bottom. They vary over time a little bit, but they vary in space within urban areas, and certainly at the regional scale. So we first kicked the tires on that, going beyond PCBs to any other semi-volatile compounds. In this study from last year with the Heights group from Indiana University, looking at emerging contaminants and being able to check out whether there's a signal. And what we found is that for most of these, the 40 or so compounds that we looked at, reducing that sampling rate uncertainty to about 7% in this first attempt. We were able to pick out urban versus regional, but that there wasn't that much variability within the urban scale that we could explain otherwise. What we've been doing lately is extending that to the global scale. This is the Global Atmospheric Passive Sampling Network run by Environment Canada. It's a global voluntary network. It's used as the primary observational and monitoring mechanism for major treaties, including LRTAP and the Stockholm Convention. And Tom Harner at Environment Canada, who does all of the lab work for this network and coordinates it, and has these global representative rural, urban, regional, polar sites, gave us their deparation results from many compounds from 2006 through 2009 and said, a year from when we start this project, I'm going to stop putting deparation compounds on any samples. So you better make it work. And so in that time, this is in preparation, we used machine learning with generalized linear models and classification and regression and artificial neural network analysis to calibrate on about 80 of those samples across 5 different deparation compounds. And so we have in the process, and here's showing for different deparation compounds, our original calibrated for Chicago bias and error using a global observational network and using a global reanalysis, we can get bias down into the single digits and error rates in the 20 to 40% range. And so in the process, and here's what that same method looks like at the global scale, everyone's been using like the one number of somewhere between 4 and 5. And it turns out, because those people had been taking these observations in the northern temperate latitudes, that's probably about right. It's not representative of everywhere else. So what we know now, and this is the 2006 average, is that there's a temporal signal based on meteorology, but there's a big wind speed-based spatial signal. This looks a lot like a wind speed map, more than, even though the model also includes pressure and relative humidity and temperature and other environmental characteristics. There's not just one number for sampling rate for any compound. And there's not just one number for sampling rate for any individual sample. It varies across compounds. These are both predictable in first principles. And so this is in preparation, and when it comes out, we're releasing it along with a web page that if you put in when and where you sampled and what you'd like to sample, we put out sampling rate within a minute or so. And so this is going operational, and it reduces the flow rate estimates from about $500 per sample to free in this case, and reduces the uncertainty in terms of bias to less than 5%. So we needed to do that to be able to understand what our samples told us, and this is we took the results of that method as a way to get an emissions inventory. So we still don't know where sources that contribute to that total PCBs in Chicago signal come from. We know a few of them, but like in terms of where are they located, how would you clean them up? No clue. And so why can't we just do this like all other air pollutants? I do this for lots of criteria air pollutants. You come up with an emissions inventory, you simulate the chemical transport and deposition process, you evaluate the emission controls, you implement the policies, and then you monitor to see that your policies were working. What we've been doing is only steps 2 and 5 because we don't have an emissions inventory and we can't evaluate the emissions control and remediation policies, and we can't use this to iterate on whatever the best policies are. So we can do that if there's an emissions inventory. And when we began this, there was one other city in the world that had one, which was Toronto. And we said, Toronto has a similar land use history, similar manufacturing history. It's about the same size and population. We can follow their methods. But they had only done so for 2 sources, which they assumed were the biggest sources: electrical transformers and building caulks and sealants, in which PCBs are used as a plasticizer. And so they were able to come up with this, but they didn't use this inventory directly in a chemical transport model and figure out how well it worked. They used results from their air sampling instead to condition a 5-kilometer scale model. So we wanted to come up with a better way. And so we first looked at all of our individual known sources, figured out where they were in relationship to our sites, and applied chemistry. So we went to the literature and into our environmental samples and either compiled or measured or estimated the source concentrations from any possible source. And then we figured out where those sources and activities might happen and how much, and calculated source-specific emissions rates for every compound in a way that if we had the same publicly available data for any other city, we could do so at the scale of each individual building and parcel. And so if we can do that for Chicago, we can do that for any other American city. Do this in a way that doesn't require local boots on the ground to go and measure stuff. Get something that leads to being able to make a national and then global emissions inventory in the same format. So really simple idea: any city, any semi-volatile compound, a few weeks of GIS by a local GIS person. That was our goal. And so we looked in the literature for source data for everything that we knew is in the environment, other than we didn't include wildlife or pets, although we did include the human body burden. And we probably should have included cats and dogs because they have high PCB body burdens. But we looked at sealants, transformers, contaminated urban soils, known contaminated sites, confined disposal facility, and that Chicago River, in-use paint, paint being sold, landfills, sludge drying beds, and people's body burdens from many different sources. And we distributed them using GIS to individual buildings. We looked at what buildings were built during the golden age of PCBs to figure out where they might be coming from. Tried to do the same thing with building area, building surface area for paint, both paint on the exteriors of buildings as well as interior. Any organic pigments, especially yellow or green, will have some level of PCBs and very replicable profiles, so that if you know what color and type of paint is being sold in the city or being used in a neighborhood, you can have a reasonable estimate of what the PCBs coming off of those buildings will be. And of course, with paint, unlike other contaminated sources, you're spreading it really thinly, you're waiting for it to dry. It's very easy for stuff to volatilize off of it. And so here are our results. This is aggregated to the city of Chicago. We found that that first guess from Toronto was about right. Transformers and building sealants are the largest sources. Soils, known contaminated sites, much smaller. And I had to go to this log scale to find paint and body burden and sludge dry. Tiny, tiny stocks out of this total of around 300 tons. And then we took that model that we developed to go from the air to the puff, and we inverted it. And we said, oh, this is now starting to show some math, but we did individual congener-specific estimates of what would happen going from the built environment out to the air for each PCB congener. You can see the relationship between that sampling rate and molecular weight. And these are the emissions. And they're a very different story than the stocks. transformers, we had to estimate the leakage rates, and are they being warehoused outside or indoors, and how old they are, and what is their concentration of dielectric fluids in PCBs. They're still a big source, but they're not the biggest. It's urban soils, and then about 20 to 30% from known contaminated sites. And then paint, which was tiny as a source, shows up big in emissions. Landfills and human body burden are non-negligible, and then municipal sludge drying. So when you have a sludge drying bed, much like paint, you're trying to expose it up a lot to the air so that it dries quickly. And the biosolids are then used locally, disposed of, or sold. And in the case of the Metropolitan Water Reclamation District of Greater Chicago, an increasing percentage of those are sold as a soil amendment for use throughout the region. So if there are any PCBs that remain in the solid form and don't volatilize off, they'll go and be emitted, volatilized elsewhere. We tried to add error estimates and uncertainty bars on these, and it turned out that transformers are the biggest source of uncertainty and variability in contamination in urban soils. Your typical backyard, typical park, is the second largest source of uncertainty. We compared to Chicago to the prior study in Toronto, and to how if we allocated to population exclusively from a national use or production scale. We found about the same as Toronto, and quite a bit less than if we just took national stuff and allocated by population. And then I used a box model to see if total PCBs, individual PCB compounds like PCB11, how they would match up to our observations at the Ogden network, and they match really, really well. So we're in the process of looking at locally and across congeners exactly how well that is and improving this emissions inventory. And we have lots of known sources giving us more information about exactly what they're doing so that we can update year by year, like what sludge drying activities are, what the volumes are, what the amount of paint being sold, so that this can become an annual inventory. And I'll show some results. So that first guess at the national scale that PCBs in population are correlated, and that's your spatial surrogate, not a very good guess. R squared is almost 0. And so this is allocated by our inventory, highly concentrated in a few areas, and this is population. They're not the same. And a lot of these places with big hotspots are areas where they're just warehouses of PCBs that are known in the national inventory, in transformer inventory. We then looked at emissions by using census tract level demographics, and we compared total stocks, total emissions, PCBs, and total TEQ. This is allocated to a 1 kilometer grid from that parcel scale, but we can do this for any building or parcel, and compared it to senior citizens, young people, people who are impoverished or low income, minorities and disability, both individually and combined. And what we found is that there's very little relationship between any of those and the total city scale, which is very different than the story of Superfund sites and contaminated sites where nearby there's poverty. At the city scale, that's not the case. So right by the most contaminated sites, sure. But when we looked at this 1 kilometer or census tract scale, whether we looked at the top 50 grid cells, it's about the 99th percentile. Top 10 grid cells, they weren't especially correlated with anything. In fact, they were in places with relatively low population. So old industrial sites, not near people. when we looked for any signal, the only thing that we found was that PCB11 coming from paint tended to be correlated with, after adjusting for population density, tend to be correlated with wealthier, more Caucasian, or more diverse gentrifying areas. So places where there's more recent buildings being built and more paint being used, that's where there was an obvious signal. But it's very different from an environmental justice perspective. At the urban scale, which is saying, for the most part, everyone's being exposed to about the same amount from local sources as compared to the worst of the worst contaminated sites. So our recommendation as a result of this is to fight the fires, not the forest, which is the source. The policies to date have focused on the most contaminated sites or transformers and other really big sources. And in fact, our evidence is that that has worked, and now what's remaining in the environment that we can see are these dispersed, lower level, smaller scale sources. That paints and pigments have an outsized impact, and that sludge drying has potential to be a large fraction of emissions. And it's been really gratifying to work with professionals from across these industries who are interested in this and to try to figure out, now that we've cleaned up the most contaminated sites, how can we address everything else, which is now responsible for a lot more of what we're seeing and for a lot of the reason why air concentrations haven't been declining the way other concentrations in other media have. So this was an e-posted note, and it got some press, and my favorite part was that it was uploaded to Reddit and not by us. I don't know how much time I have to talk about local scale, but we used AirMod, which is the US EPA regulatory approved model for individual sites for the Indiana Harbor and Ship Canal, because this known area of concern and contaminated site has many residential neighborhoods nearby, and there's a middle school and high school right near the confined disposal facility with really high PCBs in the local sediments. And currently being part of a long-term navigational dredge, navigational rather than environmental. And so that confined disposal facility is currently being filled. And the local community wanted to know how much of an issue is this for their air. Is the site currently giving off lots of PCBs and other contaminants? Will it give off more if there's dredging? 11,000 residents were evacuated this fall because their soil is contaminated with arsenic and lead. It's the next Flint. And so we did some work to model the air-water sediment exchange. There's lots of math involved. We were able to come up with a total mass balance budget. And then by looking at the PCB concentration correlated with, as it changes with sediment depth and estimated year that that sediment was deposited, figure out what the emissions might be depending on how much of it, at what layer did you dredge down to. So we used AirMod. This is generally what the result looks like. This is the annual average concentration, and you can see that based on wind speed and wind direction, most of the stuff goes off over the lake rather than to nearby communities. And in fact, we were able to conclude that the contaminated site is probably responsible for about 15% of airborne concentrations, the rest being from all of the other nearby sources as well as being downwind of the city of Chicago. Our next application has been in New Bedford Harbor as part of a SUPERFUND supplement, and there New Bedford Harbor is estimated to be the single largest source of PCBs to the air anywhere in the world. Not that it's known to, it's just we haven't found anything that's larger. And we were able to tell that it's more like about 80% of PCBs in the air there, and that this is also article in preparation. And so our goal for the next 5 years is to teach US EPA and other regulatory agencies how to approach PCBs like criteria air pollutants and like criteria water pollutants, to be able to come up with inventories that we trust, to to be able to follow this approach and to have monitoring instead of being a means of figuring out where emissions are happening, have monitoring being a way of monitoring the decline as effective policies are implemented. We're currently bringing this high throughput approach to be able to look at personal care products, emerging contaminants, and congener-specific PCB stories in that regulatory framework, including all of the oxidation and atmospheric chemistry and photolysis, as well as all the processes. And this is an example for a personal care product. This is D5 siloxane with a population-based inventory, where we're figuring out how to do this for any semi-volatile compound and then being able to use whatever we can get from local land use, local inventory development to fill in the blanks and be able to rapidly, high throughput, estimate, compare to observations, evaluate, come up with a better emissions inventory, and figure out, based on the remediation costs, a lot of which come from this group, what the best ways to clean these things up might be. So that's what we'll be doing. I've tried to play around a lot with my own personal exposure history in Chicago and those of my parents and grandparents based on the industries they worked in and where they grew up. And so this approach is a head start to being able to look at our personal exposomes going back multiple generations and figuring out the effects on metabolism, endocrine growth from your parents, their parents, and you integrated over time. With the hope that, again, because I care about Chicago a lot and we have this really large monitoring network there and great institutional partners throughout the area, that this is one of the first places that we'll be able to look at that at a population scale. We're also doing a lot to try to bring this stuff out to the web, make it accessible, let people play around with, if you reduce emissions from this source sector, how much would it cost, how much would it matter? So we have opportunities to collaborate. We have a wide selection of archive samples. We have a similar, although not as impressive, analytical laboratory setup. We have source and emissions estimates and are able to come up with those for any other areas at the individual local site scale, 100 meter or so, building parcel out to the airshed scale. Of course, multi-scale chemical transport modeling, policy analysis, and our outreach. That's the Hornbuckle Lab and collaborators, our many collaborating institutions, and I'm delighted to take questions. Sure.
So you mentioned cell interaction with regional lab. Can you tell us a little bit about their interest in
Sure. So one of the funding sources for this work was a Great Lakes Regional Initiative activity coordinated by Region 5. And they have asked for our data. I've handed off maps every time we do an update to go from our 2008 base inventory until now. We hand off our data. Anytime we come up with a new finding from it, we let them know. There has been some interest in being able to do that urban scale, local effects from individual contaminated sites, and especially from GLRI cleanups to monitor the air and to figure out how much of this change is coming from a known one or more known sites.
Any other questions here? I was going to ask as far as cleanup of the biosolids. Is your lab doing any work on that, or others that you know of, or what's the approach they're looking at there?
So, sure. So the question was about biosolid cleanup, and Iowa Superfund focuses on bioremediation through plants and rhizomes. There are other groups across the country that also use fungi, and we're very interested in looking at how that works, how much it costs, how it varies based on the type of biosolid or sediment and its indigenous microbial community, the potential for dechlorination in situ, how long it takes, how quickly it works, so that we can look at it from not just a laboratory or pilot site level, but figure out at a large-scale policy level how much can it be effectively used.
It seems these PCB molecules are just moving from the water to the soil to the air, and just they don't seem to go away. Do we have to find a way to actually destroy the molecules, or if we don't want them to just stick around for the next 500 or 600 years?
Well, so because they're semi-volatile, if we want to ask where in this multi-compartment system they will end up, will they just cycle locally? The answer is that once they get into the air, they gradually hop their way up to the poles. And that's why they were first found, this big story of PCBs 50 years ago, first being found in the poles and in polar bears and in orca in high concentrations. Eventually, over that 500 to 1,000 year time scale, they'll all make their way up there. If you want to clean them up before then, we'll have to find some way of dealing with them, either in situ or confined disposal or incineration or some other treatment. Absolutely.
Any other questions here?
Yeah, you mentioned high levels of PCBs in sludge and biosolids, and that they were a soil amendment. Have there been studies to see what types of food crops take up PCBs?
Yes, in fact. So looking globally, in the past 2 years, there have been studies of how much is taken up and how much is dechlorinated or otherwise broken down by wheat, by rice, by quinoa. So that's an ongoing, totally different set of research institutes and funding sources, but it's happening, and we know enough to know that there's a lot of variability in how much is taken up by different food crops. And we know a lot from both US and Chinese, and especially the best data set now is Korean, the PCB concentrations and congener profiles in lots of foods. And my big story here is that chocolate cake and chocolate have really low concentrations of PCBs, so they're very healthy. You should eat them a lot.
And also, I was wondering, I understand in the Chicago area there's a car shredder that years ago piled up a big mountain of residues that contain PCBs that's just sat there and apparently has blown around and stuff. Was that one of the places that got looked at all?
We looked at landfills, and we tried to estimate the known for each of the landfills in the area, the depth, when it was used, but that's a major source of uncertainty. The only way that we can get an estimate of the source or emission strength is from monitoring the air nearby, downwind, and it's a big growth industry potential to figure out exactly how much is in landfills and how long it would take for them to just blow off. Absolutely.
So, is it right that the transformers, paints, and biosolids, are those the three major sources?
That's what we think so far. This inventory explains observed concentrations in air, and it explains observed congener profiles. What we haven't looked at yet is how much it explains after we put it through a chemical transport model of that distributed urban spatial signal. And once we have done so and done emissions inversion back to the places and times where individual congeners were emitted and compare that to the congener profile from those different source sectors, then we'll have more confidence on is that correct. But at least to order of magnitude and sort of within plus or minus 10% in this NAIVE inventory, probably. It might be different in other cities, but at least in Chicago, this is the case.
So didn't they stop using PCBs in transformers and paints for how many years now? Since when? So when they stopped using those, did they find a way to destroy those materials, or what are they doing with those materials there?
So transformers in the US there's no policy that requires them to be destroyed. The Great Lakes bilateral toxics initiative on the Canada side requires, from a regulatory perspective, knowing where each transformer is, knowing where testing buildings for their contaminated caulks, and coming up with plans to actively destroy them or dispose of them in a known way. On the US side, we have a voluntary transformer inventory. We have no program for caulks and building materials. So we have a start at knowing where these are, but in different jurisdictions, there are different degrees, and there's no coordinated plan to getting to a PCB-free world for legacy electrical equipment or building materials.
So are these mostly ending in the hazardous waste landfills?
No, they're not mostly at hazardous waste sites. They are at places like Metra stockyards with old equipment and old trains, and warehouses spread throughout the city, and brownfield sites that are currently in use or recently in use. At least this is just with the voluntary inventory. So these are the ones we know of.
And then you mentioned that there's going to be some more, you think, legislation coming about in the next couple of years, hopefully to get EPA or others to have more of a plan on these issues?
The legislative angle has been because of celebrity clamor and demand from individual school districts across the country, where it often makes sense if you have a school that was built between 1930 and 1979, that's most schools. If you know that you have a PCB problem, it's probably cheaper to build a new school anyway than to try to keep that school going, maintain it for another 20, 30 years. So it's a big deal. And without a reason to test, schools go toward not testing. Not testing in air, not testing materials, not remediating. So the push will be for, on the legislative side, less for all sources and more for schools and other public buildings.
You mentioned 1930 to like 1979. We've heard, and there's some information on the website, that it's 1950 to 1979. Is it really they were used in schools and other buildings in the 1930s?
If you look at all sources, and our study has not, for outdoor in total, has not included light ballast because we had no way to come up with the fluorescent light ballast emissions. Some of those sources in schools, light ballast, paints, building materials and caulking, transformers, some of them were in use as early as the 30s, especially in insulation and dielectric fluids, some of them not until the 50s.
Okay, that's very good information. Are there any other questions here?
Some of the papers I've read that are looking at some inventories and trying to find where the sources are, specifically in caulk and paint, said that of samples taken, maybe from like buildings, maybe 50% turn up PCBs in caulk. Does that agree with what you found, and how are you modeling not only age of buildings, certain type, but what fraction of those buildings will likely have PCBs?
So we look at, and this is a big part of having City of Chicago as a partner, providing their publicly available data and getting a data agreement for everything else that they have, and looking at it from a planning perspective with their planning office. They were able to tell us when buildings were remodeled as another way of estimating for each of these different ways. We assume that if there's remodeling, they'll probably get rid of the sealants and probably add more paint. But it was more through that approach, and we've also played around with using results from sampling in Toronto, in San Francisco, and in Germany in terms of what percentage of buildings built within each set of years in those places ended up having which levels of PCBs with above TSCA 50 part per million in caulks. So yeah, we've experimented with ways to do that without individual site-specific samples everywhere.
So you talked about one of the way for remediation is biological method. What are other methods that you're finding that people are using in other countries for remediation? Is it like thermochemical, or is it like mostly landfilling? What are the ways people are taking?
So the most recent PCB workshop was held a month ago in Japan. And Japan has a giant thermal plant for their national PCB program. And it's 2 city blocks, multiple stories for incineration and capture. In China and Latin America and Canada, there's been lots of work on bioremediation in situ with switchgrass, with mycorrhizal options, with finding which existing sediments and microbial communities can work, and can you inoculate contaminated sediments with them.
Do we have any other questions here?
Biological remediation, like with switchgrass, what happens to those materials, like once it gets into the soil, or if it's used for thermal energy generation or something like that? Will it not gain impact?
So in this case, with plants, you go from PCBs to metabolized PCBs, either hydroxylated or sulfates or other metabolized products that you (50 to 100% dechlorination over time), and that would lead to there still being metabolites and breakdown products of varying toxicity that you'd need to consider if you were to use that as a biofuel or dispose of in situ. Absolutely. It doesn't get rid of everything toxic. It just moves from PCBs to other metabolites.
But it's a slow process, right? Otherwise, they would have taken care of all the PCBs through the pipeline.
A lot of the lab work is trying to figure out how to manipulate the environment to make it a faster process. But thus far, a month is fast.
I guess my question was a follow-up to that with the switchgrass. If you were to burn it after it had been growing in PCBs, would it, go into the air, or would the temperature break down the PCBs, or would it have to be very high? If you were to use switchgrass as a biofuel that had grown in PCB.
It has to be very hot. You'd have to be in a gasified thermal to be able to get the temperatures high enough. Again, you wouldn't be dealing with PCBs being emitted directly. It would be their metabolites and breakdown products in an unknown range of those at this point. So maybe.
Needs more study.
Yes.
And I have one last question, then we'll finish up. I was wondering, you mentioned that paints even nowadays have PCBs, particularly the ones with yellow dye and green dye, I think. Is there any efforts being made to make those type of pigments without PCBs?
Yes, on a research level, globally, and in places like Sweden and Japan that regulate levels of PCBs in paint, their industries are leading the way toward finding ways to reduce concentrations from what happens in the manufacturing process.
Great. Okay, with that, we'll end today's seminar. And again, I want to give a big thank you to Dr. Spak for coming over and being our seminar speaker today. Thank you.